Today we're going to be going over multi-class classification. So now let's assume, like usual, we have our set of points, xi, yi, we have n of them, and as usual, x is going to be an m-dimensional vector, but for multi-class classification, instead of being binary, each y is actually going to be a vector with a 1 somewhere indicating what class that point xi belongs to. So in this case, for example, this y would be indicating class 3. And so the way that we'll write this, it's going to be y is element of 0, 1 to the k, because there are k classes that we're concerned about. So we wish to model the probability that y is in class k given x. And before we do that, we need to introduce a function. We need to introduce the Softmax function. This will be useful for modeling probabilities for multi-class classification. So the Softmax function, as input, it takes in a vector, and as output, it also returns a vector. Let's write the form of the Softmax function. So we can use sigma for the Softmax, sigma of some vector z. The jth element of that is going to be equal to the exponent of z to the j over the sum over all the elements in z exponentiated. So for example, the softmax of the vector 1, 2, 3, that's going to be approximately equal to 0.09, 0.24, 0.67. So you'll notice that what that did is it took our largest elements and it blew them up, it magnified them even more. And that's where it gets its name from. It gets its name from taking the maximum element, indicating what the maximum element is. So it's called a soft max. And in the limit, the maximum element becomes 1. So now that we have a softmax function at our disposal, let's use it to represent class probabilities 1 through k. So we'll say that the probability that y is in class k given some x and some weight vectors. So let's just talk briefly about what these are. So as opposed to binary classification, now we have a different weight vector for every class. So that W set is a collection of all of our weight vectors 1 through k. That's going to be equal to the softmax of all of a linear combination of all the weight vectors in our input point. W2 transpose x. We're just going to take all the dot products, and whichever one magnifies x the most, that's going to give us a high probability of x being in that class. And we need to take the kth element because we want the probability that y is in ck. So to write this out using softmax, this is going to be e to the wk transpose x over the sum of every element e to the wi transpose x. And another way to think about this vector is if you were to take all your weight vectors, all your w's, and put them in a matrix. So it's w1 was the first row, w2 is the second row, all the way down to the w of your last class. Well, that vector inside the softmax would just be equal to your w matrix times x. Okay, so now that we have probabilities modeled like so, what we need to do is talk about how we might solve for the optimal w's. So how to find W1, W2, WK given our data. Given our data Y and X. So we want to learn from our data. So let's define the likelihood function. Well, likelihood is equal to the probability of seeing our Y's given our input X and our W vectors. That's going to be equal to the product over all data points N. And I'm going to write something a little bit strange here, and I'll explain what it is in a minute. Product over all classes K of e to the, now we're going to write our probability that Y is in class K over, so probability that Y is in class K, that Yn is in class K, so xn's here. We're going to raise that to the Ynk. So that does is it's only going to count the K that corresponds to Yn in the training set. So this will be 1 when Yn is in class K from the training set, and 0 otherwise. And since we're taking a product, anything to the 0 is 1. It just gets essentially ignored in the product. So that's our likelihood function, and we want to maximize that. We want to maximize the probability of seeing our data with respect to W, which is our variable, our parameter. So as usual, we're going to minimize the negative log likelihood because it makes the math easier. So minimize negative log likelihood. And this is going to be our loss function. We can refer to it as a loss because it's the negative of the likelihood. So let's write this down. The loss function of our entire set of W's is going to be equal to, now I'm going to put a negative sign and we're going to take the log. So those products are going to become sums, n over k. That exponent's coming down when we take the log, and I'm going to even use the quotient rule for logs all in the same step. So log of the numerator, so there's quite a bit going on in this one step, and if you want you can break it into multiple steps on your own, but I'm going to write it as log of the numerator minus log of this denominator. And that's all underneath the sum being multiplied by Ynk. And I think maybe we can even simplify this a little bit more, this negative log likelihood function, or at least break it up into a way that will be helpful later. Ynk, and then the log of e to anything is just anything, so Ynk wk transpose xn, and then plus, I'm going to distribute that negative through, plus Ynk log of sum over all I e to the wi transpose xn. Okay, so this is our negative log likelihood. This is our loss function for softmax classification. And now we want to take the gradient. We want to minimize this negative log likelihood using gradient descent. So we're going to, and if you're not interested in this part, you don't have to watch it. If you're satisfied with just understanding the basics, the loss function, if you want to stay tuned, we're going to walk through defining the gradient here. So we're going to take the gradient of the loss function of our W's with respect to a particular vector Wj. So I'll just put in parentheses, this is respect to a particular vector. and then we're going to perform gradient descent. On our loss function using its gradient. So let's go ahead and try to figure out what the gradient of this loss function is. So gradient of our loss function with respect to a particular vector wj is equal to, well, let's just take a look at the first term in the loss function. Keep the negative, sum over n, and then if we're differentiating with respect to wj, what's going to happen is that ynk term will only pick out ynk when k is equal to j. So we're going to have ynj xn, because that all those other wk's are constants essentially, and wj is the only thing we really care about. So we're going to pull that out. And then moving on to the second term, plus sum over all n. And here what we're going to do is we're also going to notice that the only thing that depends on k is this ynk term. And so essentially what that's going to do is it's going to pull out exactly one of these log terms. So just to remind ourselves, sum over all k of ynk for any given yn is going to be equal to 1 because it's a one-hot encoded vector. So that's going to just reduce to the sum over n. We can get rid of the k, log of the sum of exponentials. And this, we can't simplify this neatly at the moment. And so actually that's not the derivative, that would be the function before the derivative. So let's take so let me just make a quick note of that. So this becomes, the second term becomes n log of e to the wi transpose x. And so the derivative of that, well, we'll take the derivative of a log. So we'll take 1 over whatever's inside the log, first of all, e to the wi transpose x times the derivative of e to the wi, the derivative of that sum with respect to wj, and then times x, and these x's should have n's on them. So let's simplify that even a little bit more if we can. Let's put it all under one sum. We'll put certain terms together, e to the wj transpose x over the sum of exponentials minus ynj, that whole thing, times xn. And now notice that this, by definition of the softmax, this is the probability that yn is an element of class J. So this whole thing here, this whole term, is the difference, and we've seen this with binary classification as well. This pattern keeps coming up in the gradients. This is the difference between our predicted value and the true value. Oops. The difference between our predicted value and the true value. And so what this gradient is going to do is it's going to choose the points that are off the most, the points for which your prediction is farthest from the truth, and those points xn will contribute the most to the gradient. So now let's define gradient descent for the softmax classification. So the first thing that we're going to do is we're going to initialize all of our W's. And then we're going to do many iterations of descent. So for many iterations, we're going to go over all of our classes. So for we'll visit every weight vector separately. So for every class, K, what we'll do is, let's say WK at the next time step. We'll update that. Take the current time step. We'll subtract some step size times our gradient with respect to that weight vector. And we already know what this is because we just solved for it. So after that, we'll have our W's, and hopefully they'll be optimal if we have the right step size. And then the way that we'll label a new data point after training, so this will be after training. The way that we'll label a new data point is we'll take the argmax of our softmax function of the final W matrix, which we received in training, times our new data point. And so just to remind you, the W matrix, I'm stacking the W's on top of each other. So this is W1 final, W2 final, all the way down to WK. All right, so the inside of the brackets here gives you the probabilities, and then taking the argmax says I want to predict the class with the highest probability. All right, that's all we have. Thanks.